Good afternoon. I'm Peter Chang, and I'm a senior software scientist at Diamond Light Source. Right, Diamond is like the SWMR. It's a synchrotron light source, and it's built over 10 years, about 12 years ago. And we have many beam lines, and at the moment we have about 32 beam lines. One or two are either in some state of being rebuilt or being serviced, and I think one or two are still in development. We have also 11 electron microscopes, and we have lots of people come along to do experiments. 12,000 experimental shifts last year up to March, and 6,300 visitors and quite a few remote users too. So the data at Diamond, this must be similar at all facilities, is basically going up exponentially. And as you see, we passed 1 petabyte about 5 years ago, and we thought that was a big thing, and now we're close to 18. What is the motivation behind all this data is that, well, we've got to cope with large data. The volume of data is increasing exponentially, as you see, and all the detectors are getting bigger, getting faster, having more detail in them, and needing more computation to actually visualize them too. Also, there's increasing automation at the experiments, so then you can take more data more quickly, usually with robotics. So what we do at Diamond is we're trying to use HDF5 to record the data, and these are 3 detectors that we have in various states of utility. Excalibur is used in at least 1 experiment, and that's a 3 megapixel camera, and that can go up to 250 hertz. So that is, let's think about this, about 1 gigabit a second, roughly. Recording the Eiger 2, the Vectrus new generation X-ray detectors, we have, I think, 2 16 megabit pixel cameras, and those run up to 500 hertz. And this new development here is a large area time resolve detector that's in development at the moment. It's a big part of a project with the SDFC, and when we use these detectors, we actually use this new framework, which is a collaboration with our funding body, and who also fund other facilities like the neutron sources and astronomers and particle physicists. So Odin is a framework that A, controls the detectors, and B, writes detectors from them and does some light processing. And in the next slide, you see this is the architecture of a particular implementation of Odin for the Excalibur detector. And as you see, there's the area detector plugin, AD Odin there, and that gets talked to by epics, and that triggers various connections here. And one of them, the key one, is that Excalibur has UDP sockets, which the Odin data nodes read from. And that in itself writes to the files in the end. And one reason we have so many nodes is because we actually can saturate network links. So we need to fan out all the input-output to independent network connections. And all these eventually talks to GPFS, which is a cluster file system. This is another schematic, and this is for an Eiger 4M. For 16M, you have to scale up with more Odin data nodes and writing more frames and sets of frames into HDF5 file. And as you notice, on the endpoint, all these separate files are pointed to by a virtual data set. So this is part of the Odin data node, and it has a frame processing, and even the frame processor has, you're allowed to have a set of plugins, and one of them is the frame writer plugin. And it can do compression on the fly. It writes directly to the HDF5 files using chunks, and it's, well, we support virtual data sets and SWMR as well. In fact, I think Diamond was one of the sponsors of both these advanced features, and we utilize them reasonably heavily. So how much is this used around Diamond? This is an old slide, and as you see, there's various colored status blobs on the various beamlines around the ring, and you see there's a few green ones, but I guess about a quarter of them are using predominantly NeXus, and then the orange ones are in a mixed weird hybrid states where you have the metadata written in NeXus and the main data recorded in some legacy formats. So now we have 38 beamlines currently active, and of those 28 write NeXus now. 10 are still not writing NeXus. 3 of those are MX beamlines, so they write CBF. 3 have proprietary cameras running on Windows, and they write lots and lots of TIFFs. 3 others are infrared beamlines, I think, and they have their own acquisition systems based on Windows and write their own formats. And I think one's at least a electron microscope as well. And the ASCII one is a power diffraction beamline. Never mind. So out of those 28, we have 13 that write better NeXus than the basic NeXus. So we have more metadata items, better classes implemented, and a fuller reflection of what is recorded on beamline in a high standard. On top of that, we've got this new project that's just been finished, I think, and that will even improve the quality of NeXus being written even more for both old and new types of NeXus writing that we do. And that consists of a templating engine, which takes in a static template that you define in, I think, YAML, and it adds more NX entries that can basically comply with various application definitions. And it's allowed to link to dynamic datasets and add in static datasets per file. So we use these NeXus, these HDF5 files and NeXus files to basically facilitate live visualization of grid scans. So this is a particular experiment where I think this is, so there's an X-ray, there's a microscope image in the background of some cells, and there's X-ray beam scanning across a stage, and we're taking X-ray fluorescence data, I think. So you can basically tag all this data in various ways and be able to perform live visualization. So you can actually define custom scans. So in the bottom right, there's a spiral pattern, and that can define the scan points being used, and then the acquisition software will come along and do that scan for you, and you'll get that fed into the display and then displayed later. And you can see the various spectra on the bottom pane of that GUI. So, so this GUI actually is utilized in quite a few different techniques, and it's all fairly standard within Diamond, and it's because we apply to various standards, then it has a consistent presentation and a uniformity, and doesn't actually need application definitions at this point, because we're not really doing any processing. Yes, there's various issues with SWMR that I think this new pure full swimmer would basically alleviate these issues. But one of the issues we have is because we don't let every machine in our network access the cluster directly. Most of them are mounted by NFS, and that is not POSIX compliant, so we have various synchronization issues. So our visualization and processing software usually, live processing communicates via this web server that you can see that connects to the Dawn visualization, and that basically gets around this issue of unreliable data access. So on top of the visualization, Dawn has a processing pipeline in it, and we could do various data reductions using that, including Saxon wax, X-ray, fluorescence, X-ray diffraction, Zanes, and reciprocal space mapping. And all these do rely on the application definitions. And they also record information according to the class that Armando just mentioned in the previous talk about the NX process. We have other analysis programs at Diamond, and one of them is this framework pipeline, another pipeline, but this one's in Python rather than Java, and this does reduction of tomographic scans. So this is where you have a large field view with your X-rays, and you take images and rotate a sample. And so this gives you big grids of data. They're hundreds of gigabytes in size sometimes, and so this gets put on a cluster, and this pipeline would use MPI and the parallel HDF5 library to do all the analysis, and it can translate other files. So this is not just for files from Diamond, but for other facilities, and it can translate those to more NeXus type inputs that the pipeline expects. One further program we use is something called TypePy, and we use an application definition that we contributed to NeXus. Macrocrystallography can use some application definition, but it can't use the more advanced features of HDF5 at the moment, partly because most of the third-party packages can't read the new format. Also, one of the manufacturers, Detris, has its own format to cope with the multiple files being written by the new dissector. And we also write that as well to help other third-party analysis software work. So these are the issues we have with HDF5 and a bit of NeXus, I guess. Mostly it's third-party software that we have to support, which scientists expect us to be able to run on their data. Multi-threaded access for reads is quite an important one for various programs where they want better performance. There's problems with tuning of MPI on plus file systems. Getting the chunk sizes right for various techniques can be problematic. Some people encounter problems with non-unit slicing when you're reading large data sets, multi-dimensional data sets, and various issues with so that you probably quite want to know. So in the future, we have a NeXus working group that's basically drivers on to put in more and more metadata, including a description of the whole beamline from the beam, the source, to the optics, to the experiment. And part of that is because of this fair data access policy that we are being encouraged to adopt throughout all scientific community, not just light sources. Another project is to populate what we call ISPI-B, which is a laboratory information management system that was used first for MX purposes to record sample data before it actually arrives at the facility and then use it on afterwards. In terms of HDF5 and NeXus, we want to carry on improving what we record, not driven by the standards group, but by our own needs for analysis. And one of those is shadow masks in NX for working out where the goniometer arm is and then pre-populating the results files with this information so that it doesn't have to work it out time and time again. We want to, well, the data rates basically push us to use VDS more and more. And so one particular example is in MX, you want to basically take data at similar times when the crystal is at a similar level of damage. So what they want to do in the future is to take a crystal, shoot it one way, and then flip it over, shoot it the other way. So there's an inverse beam, I think they call it, and then do that for every other angle. And so that's non-contiguous, that data. So they want to record that, but present it in a contiguous way. So that's an example of using virtual data set. Okay, I think that's it. And thanks to these people from whom I stole most of the slides. And they will hopefully add on it, or, well, one's leaving, but never mind.
Thank you. Thank you. Time for 2 questions.
I had one, was the BDS performance, is that, I mean, it's a problem, but is it a showstopper or not?
Depends on technique, because there are ways around using VDS. You just use files directly. So that's always the workaround. Okay. Ideally, we should get to the point where you can use it directly, but yeah.
Any other questions? I have a question or suggestion for parallel. We did a lot of improvements for reading and opening files with a lot of metadata. So maybe we can talk offline how we can help with parallel performance. But I don't know if it's done through H5Py or through CAPIs of API.
We use
H5Py. So
with a parallel build.
Okay, so we probably need to involve H5Py people to implement those features. Okay, thank you.
Thanks.